Assalamu alaikum. So, in the last lecture, we introduced the course and we talked about the different components of the course, the three major components of the course, where we will be going through the basics of signals and then moving on to some biomedical signals. And the last component of the course is about medical imaging, where particular examples will be used and their applications will be discussed. This is the second lecture in those series, and here we introduce the concept of signals. Now, signals are, simplistically put, they could be one-dimensional in nature or two-dimensional in nature. So a one-dimensional signal could be a sequence of numbers which are ordered with respect to their measurements, which could be in terms of time, or in our case, a two-dimensional signal could be an image, because an image has an x and y coordinate. So for instance, this particular screen that is visible right now has a number of x and y coordinates, and each coordinate has a particular value because of which you see what you're seeing right now on the screen. The two typical examples are the grayscale and the colored. In the grayscale, each value x, y has each coordinate has a value associated to it. Now, that value could be ranges from dark to very bright. Colored images, on the other hand, each coordinate has an RGB value. So there's a red, green, and blue defined for each coordinate. And it is the mixture of these colors that gives all the colors that you see. Now, this is an example of a digital signal. And this signal is digital because if you see on the y-axis, the signal ranges between two specific values. The entire signal, if you see here, defined in time domain, has two values. One is a lower value, which you can refer to as 0, and the other is a high value, which you can refer to as 1. Now, those values do not necessarily have to be 0. As you can see here, deliberately, it's not starting from the x-axis. It's not touching level 0. It could be a lower voltage like 0.3, and a level 1 could be a high voltage like 3.4 volts. But the important take from this particular diagram is that a digital signal has fixed levels in which a value that a signal can take. As opposed, let's see this signal, which is an analog signal, where the body temperature, which is represented on the y-axis, is measured in terms of time. Now, this is an analog signal, and as you can see, for any given time instance, the signal can have any possible value between these limits. I mean, it could have 103.6, and then 103.67, and then 103.678. Point is, there are infinite number of possible values that an analog signal can take between two extremes. Once again, I do want to highlight this, that it is the y-axis which defines whether a signal is analog or digital. Now, at the same time, if we want to take samples of this particular signal at, let's say, 300 seconds, at every 300 second interval, if we take sample this particular analog signal, we get what we refer to as a discrete signal. Now, in this discrete signal, the envelope of this signal follows exactly the one we've seen here. It follows exactly this shape. But what we see here is this is defined across the whole time domain. This, however, is defined after every 300 seconds. This is 1200, this is 1500, 18, and then you can see it again at 3000, 4500. So this is an example of a discrete signal. Now, a discrete signal is a signal which is defined at specific instances of time, not the whole time, but specific instances. So for instance, this signal is defined across the whole time. As you can see here, this is only defined in particular instances. Therefore, this makes it a discrete signal. If you look at this signal, which is the last of the four, you have a continuous signal. It's called continuous because it is continuous in the time domain. It is analog in the amplitude domain, but it is continuous in the time domain. Similarly, this signal is analog in the body temperature y-axis domain. It is discrete in the time domain. This signal is analog in the body temperature or the y-axis. It is continuous in the time domain. Similarly, this signal is digital in the value here, but it is continuous in the time domain. Now, the two important principles which is derived from these four signals is this. One is called quantizing, and the other is called sampling. So this is your analog signal. If we sample it at specific instances of time, you receive a signal like this. This is called sampling. Now, in sampling, you're discretizing a signal. At the same time, if the same signal is quantized, in other words, because it's analog, there are infinite possible combinations defined in this this. So what you want is you want every value to have only is defined over specific jumps. And as you can see here, it's the same signal which is shown here, but it is quantized. Now, if we discretize the signal again, this is what we get. Similarly, if we quantize the signal, it adopts specific levels which are allowed. This particular example was a binary signal because you were only allowed 2 levels, 0 and 1, but it doesn't have to be just 2 levels. You can have more, as the example shows. An important principle that we will talk about now, but we will discuss later in detail, is what is referred to as the Nyquist criteria. Excuse me. What the Nyquist criteria says is that, so the Nyquist criteria helps you to determine the minimum sampling frequency in order to retain all the information of the original signal. If you reduce the frequency less than that, you will lose information during the sampling process. Now, there are two particular transformations. One is in the time domain, the other is in the frequency domain. So whenever you get a signal, you can look at the signal in time domain, or you can look at the same signal in frequency domain. It is important to understand is it is the same signal. The question is, what are you really interested in? So for instance, if you are making a long distance call or forget about a long distance call. Within several countries now, there is a peak hour at which making a phone call is more expensive, and there is an off peak hour where making a phone call is actually very cheap. So, for instance, some countries would provide very cheap call rates for night time because most of the people don't talk at night, they're sleeping, and there is an infrastructure out there, might as well use it. Similarly, in the electricity bills, there is a peak time where, for instance, most of the offices are open and everybody is out there working. So that would be, in some countries, peak hours. Off peak hours could be the evening time or it could be night time. In night time, everybody's sleeping, so spending electricity at that time may actually be cheaper. It depends on country to country. But it really depends. For instance, medication for children is different from adults. In other words, it's the same individual. It's just that at an earlier age, the physiology is different. At a later age, it's a completely different body. Therefore, the same individual at different instances of time for the same disease would be given a different medication. At the same time, there is something which is referred to as a frequency domain. Now, in a frequency domain, for instance, a good question could be, well, how frequently does your machine give a problem? And that itself is a good example of by which you can, in fact, schedule periodic checkups for a machine. I know the photocopying machine, or the Xerox machine, or simply put, the photocopying machine in our university does break down several times in a year. Because a lot of time paper is not being fed in properly and not everybody uses it very nicely. Now, what is important to understand is that whether you look in the time domain or the frequency domain, the signal is the same. It carries the same information. So, for instance, here Optimus Prime is the same Optimus Prime whether he is in this format or whether he's in a truck format. He is the same guy. And by the same token, really similarly, this robot here is the same whether it looks like an aircraft or he looks like a robot. The information is the same, and this is a trick question that I've asked the students sometimes. That assume a signal is given both in frequency domain, which is the Fourier domains, or the time domain. Which domain gives more information about the signal? The answer is neither is giving more information. It's the same signal. However, some signals reveal certain characteristics which are important in time domain, and some signals highlight other characteristics which are more important or more visible in the frequency domain. And therefore, it depends on what is it that you're really looking for. That was the end of the signals component. I hope you like this lecture. In the next lecture, we will be talking about very fundamentals of images, and we'll talk about the grayscales, and we'll talk about the image histogram. Thank you very much. Have a good day. Bye-bye.